In this video, we'll be covering the Ecell voltage for non-standard conditions, and it's predicted the outcome of this is predicted by what's called the Nernst equation. And the Nernst equation is really nothing new. It's something that we learned in the thermochemistry chapter. So the equation for it is this, and I'll show quickly how it's derived. So it's derived from this equation right here, and then we'll go over the explanation of how to analyze it. So this is from thermochemistry. So for any reaction that's not at standard conditions, you could analyze the free energy by analyzing Q, and it includes the free energy of the reaction when it's under standard conditions. So we'll need a way to find this, and we'll need a way to find that. So remember that and I'll remind you at the end. Okay, so we use this equation, and we use this equation, and we use this equation. That the free energy of an electrochemical cell is given by negative NF cell. Okay, so we're going to use this, and also under non-standard conditions, the free energy is also given by the same equation, just when Ecell is non-under standard conditions. So we're going to use this and substitute. So we're going to take this right here, and then we're going to plug in these numbers, or these equations for these right here. That's all we're doing here. So we're taking this, and we're going to plug in negative NF cell, and we're going to take this and do the same, but for standard Ecell. Okay, plus RT ln of Q. And then this is really it. This is the Nernst equation, but it's usually not written like that in textbooks. So usually we clean it up a little. So we're gonna divide each term by negative NF. Okay, and then we get the following. So this here will drop out. This drops out right here. Okay, and then this becomes a negative because of this. And then this term actually here, so the RTF, if you do it at 298, which usually these cells are done at around room temperature, which is around 25 C. So if this is done at 298 K, then this piece right here winds up being a constant as well. So this piece right here winds up being just the energy form of R, 8.314 times 298 divided by Faraday's constant, which is 96,485. And they usually use the Nernst equation instead of the natural log. There's a conversion. I think there's some type of conversion factor like 2.303 to convert. So usually it's written in terms of a log base 10. But this number, so all of that reduces to this. So this is kind of where this comes from. So cleaning all this up, we get this. So we get Ecell equals Ecell standard minus the number 0.0592 over n times the log of Q, where Q, if you remember just all the way back to our equilibrium chapter, Q is just the concentration of products over the concentrations of reactants. Okay, there's one key thing. So this is the common way it's written. One key thing I'd like to point out is when you're analyzing the Nernst equation, you need to figure out. So you need the half reactions, the correct half reactions, and then you'll need the full chemical equation. The full, I should say, balanced when using the Nernst equation. I'll tell you why. if you have the full balanced chemical equation, you'll have the correct expression for Q. So you'll have the product over reactants. And remember solids, you'll see like the anodes and electrodes, solids. So solids are not included in the expression for Q. Remember that. Okay, this right here is determined from the half reactions. So Q again is from the full reaction. This is from, so the expression for Q is from the full balanced reaction. N is determined from, so this is determined from the half reactions. And then Ecell standard is also determined from the half reactions. This is also from half reactions and the SRP table, of course. So looking up those and reading them correctly, that includes flipping the correct one, the one that gets oxidized. Okay, so let's go on to the next slide and figure out what this means. Okay, so let's take a look at a specific example, and we'll play around with some numbers and see what happens with the Nernst equation, and specifically what happens with Q when you change the initial concentrations of the electrochemical cell. So we're going to take a reaction. We'll take this reaction. We'll take 2 Ag, 2 silver ions being reduced by solid zinc, and zinc is going to get oxidized to Zn2+, and that will make 2 solid Ag atoms per reaction. So our half reactions are this. It's going to be 2 Ag plus 2 electrons making solid Ag. And this, of course, is the reduction half reaction, which is going to be a positive 0.80 volts. And that's our reduction. Our oxidation is going to be for the zinc atoms being converted to Zn2+ plus 2 electrons. So that's going to be the reverse of, I don't know offhand the numbered, I know how we numbered the reduction potential table, but I don't know the exact number. But that one's when you reverse that one, you get a positive 0.76 volts. So my E cell under standard conditions for this is going to be 1.56 volts. And let's see what happens if we change the numbers around, if it's not going to be 1 molar and 1 molar of Ag and zinc. So what I like to do is I like to relate this to like a battery. And I know, a lot of students, like every day you go through this cycle where you start the day with a charged cell phone, and then by the end of the day you have like 10%, 15%, whatever, and it's time to plug it back in. That whole cycle is this equation. It's the Nernst equation. So that's what's over the course of the day, your cell phone is spontaneously discharging, and you're over time you're increasing the number of products in your lithium ion battery, and you're reducing your number of reactants, and that's lowering your cell's voltage and its electromotive force, its ability to do work, to have negative free energy. You're getting closer and closer to zero when your battery discharges. So let's look at that for, now this is not what's in a lithium ion battery. This is just a random electrochemical cell, the reaction that I wrote up here. But the process is exactly the same as what's going to happen here. So let's take a look at when you have lots of reactants. So when you have, so this is when you have a lot of reactants compared to your products. How does this change Q and Ecell Nonstandard? So let's just throw some random numbers in there. So I have Ecell Nonstandard equals Ecell standard minus 0.0592 over n times the log of Q. Now Q is taken from the overall balanced reaction, so I can't emphasize that enough. You need to look at the ions on the product side and all of your ions on the reactant side. That's Q, the two things that I just circled. So Q is going to be your concentration of zinc ions over your concentration of silver ions squared. Remember, we have to square it because of the coefficient when it's balanced. So let's throw some numbers in there. 1.56, and I did this ahead of time, so I'm not gonna waste time in the video plugging in numbers into my calculator. So I have like negative 0.0592, and actually I like to use brackets on this to make sure that that negative gets distributed to this entire blob here. So my moles of electrons transferred is 2. That's where that number comes from. Times, now I just made up some random numbers here. So I said, what if we start the cell with this at a really low concentration? So 1 times 10 to the negative third molarity. And what if we started this with a really high concentration? So this is kind of like when you start your day. You wake up in the morning and your phone is fully charged. That means you have tons of this. So overnight, you actually made this cell, you made your battery run in reverse is what you did by plugging it in. You forced it to do a positive delta G process is what you did when you plugged it in. So now when you click on power, you unplug it, you click on power, now it's going to spontaneously go this way, because as we see, that's spontaneity is in the from left to right for that reaction. So let's say we have like tons of reactants and we have very little product. Now when you charge your cell phone, this number is going to be way less, like something close to 0 probably. So you're going to get a massive increase. This won't be as exaggerated as what happens with your phone, but it's a good example nonetheless. So we'll go with this. So we have log of Q. So if we take the log of this number, okay, so I went ahead and I did this ahead of time. I got this number. I got negative 4.40. Okay, and now what happens here is I get 1.56 volts, and since that's a negative, because this is a giant number and this is a tiny number, then my Q value is less than 1. My ratio for Q, what ends up happening is I get a negative value, and this negative right here makes me actually add to the overall voltage. So I'm going to be adding the number when I do the arithmetic here. I'll be adding the number 0.13 to my cell voltage under standard conditions. So this results in an increase of up to 1.69 volts. Okay, it doesn't sound that drastic because these numbers are not quite that drastic. So like I was saying with your cell phone, this number would be way, way less than that, which would improve your value of Q, which would be adding a giant number to your overall voltage. Okay, so in terms of delta G, so delta G under standard conditions, if I calculate that, it's negative NF Ecell. So if I calculate this under standard conditions, I have a negative 301 kilojoules of free energy of work. So if I do it under, if I do the same thing under non-standard, instead of, so here I plugged in 1.56, and here if I plug in 1.69 volts, if I plug in 1.69 volts, it increases my free energy or available energy to do work up to 326 kilojoules. So that represents about an 8% increase in free energy that you can use to do work. Okay, so not much, but like I was saying, this number for a cell phone would be a lot less than that, which would improve Q. All right, so raise the negative value, which ends up adding to Ecell. So let's look at another quick example. So what happens when you have your products? So after your phone has been running for a certain amount of time, your products are going to start to increase and your reactants decrease. So this is why this equation is so important, is because this is what happens with a cell. As soon as you turn it on, things are not 1 molar anymore. The instant you turn it on, your products are gonna increase and your reactants decrease. So that's the importance of this equation. So it's directly applicable to a real life situation or a battery. So what happens if you have this? So how does this change Q if you do this and Ecell? Okay, so so if I do the same analysis, but I reverse it. So what if this time my zinc concentration goes up to 5 molar? So it's been running for a while, your cell, and your silver is 1.1 1 times 10 to the negative third, and then I square this number. So I went ahead and I got these numbers ahead of time, 1.56, and as you could see, this number is going to be really, really large and positive. So your Q is going to be much greater than 1, which results in a positive number for the log of Q. And when you have a positive number, so when this term ends up being positive, this negative here actually ends up subtracting from your Ecell. Okay, I'm having a little issue with the slides. They keep changing on their own. I'll see if I could fix that before the next video. So just kind of bear with me here. So if we have a minus 0.20, okay, then my cell actually decreases to 1.36 volts over time. Okay, and if I calculate delta G for that, delta G non-standard, I end up with negative 262 kilojoules. So it's still running from left to right. Okay, it's still spontaneous going left to right, but you could see over time my free energy is getting more and more positive. So what happens when your cell runs out? So what happens if you run out of reactant? Okay, then this term right here, this term right here will actually match your Ecell standard. So when this term matches this term, okay, that 0.0592 over n times log of Q, when these two numbers match, your Ecell standard is actually 0, and then you're at equilibrium. Okay, and then your cell, or if this was like your cell phone battery, it would actually die at that point. Okay, so that's actually, I could summarize that real quick with this U, where we had free energy. So this time, instead of calling it free energy, we could call it Ecell, and then this right here would be the progress of the reaction. So if you remember this, here's where you have 100%. Here's where you had 100% reactants. And then here's where you have 100% products. Now, in a battery, you're never really dealing with this side right here. You're never really dealing with that side, because when your battery dies, it stops. So here's where delta G non-standard is 0. And since delta G equals negative NF Ecell, when this is 0, that's when Ecell is also 0. So here's where also Ecell non-standard is 0. So when your cell runs out, it makes delta G 0, and you're at equilibrium. So the battery is dead. Going back to the cell phone battery, so the battery is dead right here. So you ran. So what happens is you ran out of reactant, and you have too much product here. So when you wake up in the morning, assuming you charge your phone at night, you're way up here. Then as the day progresses, you're right here. You're going down this, down this, down this, down this, and then around 8 p.m., 9 p.m., whatever, depending how much you use your phone, then your phone dies right here. So when you plug it in, it goes all the way back up to here. Okay, and then you're on like Facebook, Snapchat, I don't know, whatever else. Facebook, Snapchat, and then you get to right here, and then your phone dies. Okay, then you got to charge it back up. Then Facebook, Snapchat, and then browser, internet, browser. Maybe you actually read a book. Facebook, Snapchat, and then it dies. Okay, and then you charge it, and then it dies. Okay, so you're running. When you charge it again, you're going positive delta G back up here. Okay, and then this is all negative delta G when you click it on because it's spontaneous. Okay, so I have a your turn, and this is to answer the Nernst equation conceptually. So let's take a look at this. So here's my cell. Okay, and so find the you'll need the standard voltage for this the cell pictured here. So, and then try to answer the questions that follow. Okay, so, and this is my hint here. So as I stated earlier on in the video, you need a balanced overall reaction. That's the key to obtaining that's the key to getting the correct expression for Q. Okay, and then keep asking yourself, what is Q exactly? So write out the whole thing in order to answer these conceptual questions. And then what is happening to Q? We'll practice the more math kind of stuff, like plugging stuff into the Nernst equation and stuff like that in class. But as far as the AP exam, this is what they want you to be able to do, is answer questions like this. Okay, but you need to write it out. If you're gonna get lost if you try to do this in your head. So you gotta write out the balanced equation and get Q. Write the full expression for Q. Okay, so. And what I'm expecting is a full explanation for your answers. Don't just say increase, decrease, or stay the same. So what happens if the following scenarios happen to your cell? What would happen to your cell voltage if you do the following? So what happens to cell voltage if the following things happen? If you add copper sulfate to this compartment, so you're adding, so copper sulfate is soluble, so you're adding solid copper sulfate to this. Okay, what would happen? Okay, and like I was saying, is I want you guys to be describing Q in your answer. What happens to voltage based on what happens to Q? So use Q for every explanation here. So for B, it says if the size of the zinc electrode, what if this is increased? So you have double the size of the stick right here inside the anode compartment. Okay, what if that's double? What would happen to Q? And then what would happen to the cell voltage? Okay, what if the anode over here, what if the anode is diluted? What if you add more water to the anode? What would happen to Q? What would happen to cell voltage? Okay, and then what if the pH is raised in the anode? So what if you add a whole bunch of like sodium hydroxide here? What would happen? I'll give you a hint. It involves the solubility, or in this case insolubility, of the hydroxide ion. So what happens if you raise the pH in here? What happens to Q? What happens to cell voltage? Okay, now for part E, what happens if the cathode, what happens if this is knocked over, some is spilled out, and then you quickly tip it back up? What happens to Q? What happens to cell voltage? Okay, so give it your best shot on that your turn. That's the end of the video.